Welcome back to Rhythm and Roots. Today we gaze at the sky and ask a fundamental question. Why is the sky blue?
That's right. It seems simple, but holds fascinating science. A phenomenon we see daily, yet rarely understand fully.
It involves light, gases, and tiny atmospheric particles, revealing the beauty of physics in action.
Absolutely. We'll unravel the mystery behind Earth's blue canopy and discover why sunrises often glow red.
Let's start with sunlight. It appears white or yellowish, but sunlight is actually made of all colors of the rainbow.
These colors have different wavelengths, from short violet to long red, like a spectrum of visible light.
Now, the Earth's atmosphere. It's crucial. It contains tiny nitrogen and oxygen molecules.
These molecules are much smaller than light's wavelengths, and they interact with sunlight in a specific way.
This interaction is called Rayleigh scattering, named after Lord Rayleigh, who explained it.
Rayleigh scattering states shorter wavelengths scatter more, significantly more than longer wavelengths of light.
Blue and violet light have the shortest wavelengths, so they are scattered most intensely by atmospheric molecules.
When sunlight enters the atmosphere, blue light scatters everywhere, in all directions, across the sky.
This scattered blue light reaches our eyes from all angles, making the sky appear predominantly blue during the day.
Violet light scatters even more than blue, but our eyes are more sensitive to blue light.
Also, some violet light is absorbed higher in the atmosphere, so blue is what we mostly perceive.
What about red and orange sunsets? When the sun is low, light travels through more atmosphere.
More blue and violet light gets scattered away from our sight line, leaving mostly longer wavelengths like red and orange.
These reach our eyes directly, creating fiery sunsets, a beautiful demonstration of light's journey.
Consider clouds. Why are they usually white or gray? Clouds are made of much larger water droplets or ice crystals.
These particles scatter all wavelengths of light almost equally. This is called Mie scattering, affecting all colors.
When all colors are scattered equally, they mix, resulting in white or gray appearance for clouds.
Darker clouds occur when they're thicker or denser, blocking more light from passing through.
What about the sky on other planets? Mars has a reddish-brown sky, for instance,
due to abundant iron oxide dust particles in its atmosphere, which scatter red light more effectively than blue.
Uranus and Neptune have blue skies. Their methane atmospheres absorb red light,
leaving blue and green light to be scattered, creating stunning azure hues.
The composition of an atmosphere dictates its sky color, a cosmic palette shaped by gases and dust.
Even tiny atmospheric particles from pollution can change sky color. Larger particles scatter more wavelengths, making skies hazy.
They can create vibrant purples or pinks at sunset by scattering remaining light in unique ways.
Understanding Rayleigh scattering explains daily phenomena, from the blue sky to the colors of a sunrise.
It connects fundamental physics to our visual experience, revealing the science behind Earth's beauty.
So, next time you look up, remember the scattering and the tiny molecules painting your world blue.
Let's delve deeper into light's fascinating behavior and how it defines our perception of color.
The angle of observation also matters. Looking directly at the sun versus across the sky
changes the amount of scattered light reaching our eyes, influencing perceived sky color.
This is why the sky near the horizon is often paler. Light travels through more atmosphere there.
More scattering occurs, making blue light less intense, closer to white.
Consider polarization of sky light. Scattered light becomes partially polarized,
meaning its waves oscillate in a preferred direction. Some animals can detect this polarization,
like bees, using it for navigation. A hidden layer of visual information.
What about twilight colors? The magic hours. After sunset, the sky glows with purples and pinks.
Sunlight reflects off high-altitude dust and particles. still illuminated by the sun's low angle.
This creates vibrant, ethereal displays of light, a beautiful interplay of scattered light and atmosphere.
The thickness of Earth's atmosphere varies. Thicker at sea level, thinner at high altitudes.
At high altitudes, the sky appears a darker blue. Fewer molecules scatter light, so less blue reaches us.
Astronauts see a black sky in space. No atmosphere, no scattering, just starlight.
A stark contrast to our vibrant planetary canopy, highlighting atmosphere's crucial role.
Even humidity and aerosols impact sky color. Water vapor and tiny pollutants scatter light.
They can make the sky appear paler or more vibrant, depending on their size and concentration.
This explains regional variations in sky appearance, a local touch to a global phenomenon.
The science of light scattering is fundamental to understanding not just sky color, but many optical phenomena.
From the shimmer of distant heat to the sparkle of diamonds, physics shapes our visual world.
It teaches us to observe closely, question deeply, and appreciate the invisible forces around us.
The color of the sky is a constant scientific wonder, a daily reminder of light's amazing properties.
It reflects the invisible interactions above us. A beautiful, ever-present atmospheric masterpiece.
Let's consider atmospheric optics in more detail. Phenomena like rainbows, halos, and sundogs are related.
They involve light interacting with water droplets or ice crystals, creating stunning visual effects in the atmosphere.
Rainbows occur when sunlight is refracted, reflected, then refracted again by water droplets, separating colors.
Halos form around the sun or moon due to ice crystals refracting light.
These complex light interactions paint the sky with a dazzling array of atmospheric spectacles.
The Tyndall effect is also relevant. It describes light scattering by larger particles, like smoke,
making a light beam visible through a dusty room, or creating a hazy appearance in the atmosphere.
It's distinct from Rayleigh scattering, involving different particle sizes. Yet, both contribute to sky's appearance.
Why is the sky dark at night? No direct sunlight reaches our side of Earth.
So, there's no light to scatter, just distant stars and cosmic darkness.
This simple observation reinforces scattering's role, explaining the absence of blue at night.
The concept of light pollution impacts sky visibility. Artificial light scatters off atmospheric particles,
creating a glow that obscures stars in urban areas, a modern alteration to our night sky.
This fascinating interplay of light, matter, and perception continues to reveal wonders about our planet.
Every color, every shimmer, every atmospheric phenomenon has a scientific explanation waiting to be understood.
Also, consider the sky's color during solar eclipses. As the moon covers the sun, the sky darkens.
The scattered blue light diminishes significantly, making the sky appear a deep, eerie twilight blue.
It's a unique visual experience, unlike normal night, showing how delicate atmospheric light balance is.
Even volcanic eruptions can affect sky color. Fine ash and aerosols scatter light in unique ways,
creating vibrant, prolonged sunsets and sunrises, a dramatic, temporary alteration of our atmosphere.
These dynamic changes remind us of constant atmospheric activity and light's endless interactions with particles around us.
The zenith is the highest point of the sky. Here, the blue color is typically most intense.
Light travels the shortest path to our eyes. Less scattering, so blue appears strongest.
At sunrise and sunset, the sun's low angle makes light travel through more atmosphere,
causing reds and oranges to dominate as blue light scatters away.
The science of sky color is a beautiful journey, from tiny molecules to grand celestial events.
It bridges everyday observation with complex physics, inspiring a deeper appreciation for our world.
Thank you for joining us on Rhythm and Roots today. We hope this dive into the sky's color enlightened you.
It's been a pleasure exploring this fascinating natural phenomenon and its scientific explanation.
Until next time, keep looking up, keep learning, and let the wonders of the world amaze you.
Goodbye for now.